everyone, this channel is talking about bulk materials. Today, this video is number 3 for method for establishing standard class and special class pressure temperature ratings as per ASMEB16.34. So we will discuss about the difference of carbon steel on material group 1.1 and material group 1.2 and material group 1.3. In the previous video number 2, I talked about the selection of the bulk rating class in the rating table in accordance with the given bulk design conditions. In the carbon steels material groups, we understood that the lower rating class tended to be selected in the material group 1.2 of WCC and LCC, and the higher rating class tend to be selected in the material group 1.3 of LCB. So, material group 1.1, 1.2, and 1.3, which are the same carbon steels, have different allowable working pressure on the rating class in each rating table. So, as shown in the attached chart on the relationship between the allowable working pressure and temperature. In case of the rating class 300. So, two charts indicate the left side chart for standard class 300. The right side indicated in case of the special class 300. So, in the chart, horizontal axis indicated the temperature degrees Celsius. So vertical axis indicated the allowable working pressure unit bar. Three material group indicated by plotted data. The red line indicated the material group 1.2. and the blue line indicated the material group 1.1. So gray line indicated the material group 1.3. So the allowable working pressure for the material group 1.2 still higher value indicated over whole temperature areas. So the material group 1.3 allowable working pressure indicated a lower value over the whole temperature level. So in case of the special class 300, material group 1.1 and material group 1.2, the allowable working pressure almost the same value indicated, but temperature 100 degrees Celsius over and more increasing temperature, material group 1.1 allowable working pressure something decreasing. So material group 1.2 allowable working pressure still constant value indicated up to the 350 degrees Celsius. The allowable working pressure for the material group 1.3 is still lower value than other two materials. But the three material group indicated constant around the 350 degrees Celsius. 350 degrees Celsius and more increasing the temperature, decreasing the allowable working pressure, rapidly decreasing. From here, we discuss about the chemical composition and mechanical property for the carbon steels. This assigned table for the specified chemical composition and mechanical property by the appropriate material specification. Assigned material WCB and A115 forging material in material group 1.1, and WCC casting and LCC casting in material group 1.2, the LCB casting in material group 1.3. So specified chemical composition assigned here, and specified mechanical property indicated here. So that chemical composition, carbon content, and silicon, manganese, and phosphorus, and sulfur. So phosphorus and sulfur element, impurity element, so that the value element is as small as possible. So that indicated specified value of the 0.035 and 0.040 something. So that the specified content value is very small, indicate. Silicon is needed for material produce, but I think the silicon element is not so affect the mechanical property. So we look at the carbon content and the manganese content, focus on the element. Carbon content indicated 0.3% and 0.35%. So WCC and LCC material specified something smaller carbon content, 0.25% maximum. LCB casting same as 0.30% maximum. Manganese content 1.0% maximum around. So WCC and LCC casting is a relatively higher specified manganese content, 1.20 maximum percent. So mechanical property, tensile strength and yield strength. So tensile strength specified 485 megapascal minimum, WCB A105, WCC casting, LCC casting. So LCB casting is relatively lower value specified, 450 megapascal minimum tensile strength. So in case of the yield strength, WCB and A105 specified 250 megapascal minimum, and WCC, LCC casting specified relatively higher yield strength 275 megapascal minimum. In case of LCB casting, lower level 240 megapascal minimum yield strength. In case of the comparative of strength level, so we consider the factor of the yield ratio sometimes. So I assign the calculated number here. So yield ratio calculate the yield strength 250 divided by tensile strength 485. So calculate number 51.5%. So A115 also same, and WCC, LCC is 275 divided 485, so 56.7% calculated. The LCB casting 240 divided by 450 calculate number 53.3%. So WCB and A105 relatively lower yield ratio value, close to the 50%. WCC and LCC castings higher yield ratio indicated. The LCB casting is 53.3 is higher than WCB A105. So the LCC casting and LCB casting both are low temperature surface application material. So ASTM A352 material specification require the low temperature impact test required. Minus at minus 46 degrees Celsius temperature impact test. So carbon steel and ferritic steel has a inherent low temperature brittleness property. So normal carbon steel is cannot be used for low temperature because of the possibility of the low temperature brittleness. But LCC casting, LCB casting, the A352 specified, so something special process conducted casting material to be good toughness at the low temperature. So if the low temperature impact test passed, LCC and LCB can be used down to minus 46 degrees Celsius. So normal carbon steel WCB A105 WCC is used for ambient and middle temperature or relatively high temperature service material. So these WCB A015 WCC material is cannot be used for low temperature. So generally speaking, that limit is low temperature is below freezing temperature. this is a normal thinking for low temperature brittleness property. But ASME B16.34 in the rating table indicated the temperature range minus 29 degrees Celsius converted minus 20 degrees Fahrenheit. So in case of the ASME B60.34 carbon steel material, normal carbon steel material can be used down to the temperature minus 29 degrees Celsius. But another comment indicated in the ASME B60.34, I assigned clipping the description, some description. So the comment in here, decreased inductivity of carbon steels at low temperature, even in application above minus 10 degrees Celsius, 20 degrees Fahrenheit. So the normal thinking, the pressure retaining material is, I think, limit low temperature is minus 10 degrees Celsius, I think. So next is we will discuss about the more detailed chemical composition and mechanical property. So we will discuss about chemical composition of carbon steels. So we discuss about the chemical composition and mechanical properties for the representative carbon steel of WCB, A105, WCC, LCC, and LCB. The attached table indicates the chemical composition and mechanical properties of the carbon steel, specified the material specification. With a focus on the carbon content, less 0.3% to 0.35% are specified for all 5 carbon steels. WCC, LCC is something lower of 0.25% maximum carbon content. I think that the specified maximum carbon content of 0.35% is reasonable for indication of not hardenability as for the barren material such as pressure retaining parts. All mass standards related on the pressure parts and materials such as ASME Section 8 Division 1 for pressure vessel, ASME B31.1 of power piping, and ASME B31.3 of process piping normally require the maximum 0.35% of carbon content of the carbon steels in case of the welded construction. I assign the related on description of the carbon content derived from ASME B31.1. So carbon or alloy steel having carbon content of more than 0.35% shall not be used in welded construction. So ASME B31.1 clearly mentioned like this. So in the welded construction, less 0.35% carbon content of the parent steel material can avoid the heat hardening on the heat affected zone we call HAZ. We look at manganese content. 1.0% of manganese is specified on WCB, A105, and LCB. WCC and LCC indicate relatively higher 1.2% of manganese content. It is said that carbon and manganese will affect increasing of the hardenability. We often hear about carbon equivalent number in process plant. This number indicated the index of hardenability in carbon steel. So I assign the relate on carbon equivalent derived from ASTM A216. So supplementary requirement 11. So the carbon equivalent equation here, indicated here, this equation is very popular equations. So carbon equivalent equal carbon. Carbon is very effective for hardenability element. Second is manganese. Manganese is also a hardenability element, but the infection is 1,6. So another element, chromium, molybdenum, and vanadium, nickel, and copper. This is also the hardenability element, but not so much effective for hardenability. So sometimes we consider about the carbon content and the manganese content. I think that in case of WCC and LCC, manganese content specified to higher value instead of specified lower of carbon content to suppress carbon equivalent number. So if the supplementary 11 specified the casting material, so WCB casting specifies the 0. Carbon equivalent number 0.5% maximum to be controlled. WCC casting carbon equivalent 0.55% maximum to be controlled. But in process plant, very often requires a NOS requirement. In case of the NOS requirement, carbon equivalent number specified 0.43% maximum. 0.43% maximum is relatively severe requirement. So we have to purchasing the related material to the supplier with the special specification of the carbon equivalent 0.43% maximum to be controlled like this. So the carbon equivalent is something consider the in process plant. Second is mechanical property of carbon steels. We look at the mechanical properties. 485 megapascal converted 17,000 psi minimum of tensile strength is specified on WCB, A105, WCC, and LCC. 450 megapascal converted 65,000 psi minimum of tensile strength is specified on LCB. WCB and A115 are basic barrel materials and used to be from before, I think 485 megapascal, 70,000 psi of tensile strength is basic strength of the barrel material in ASME B16.34. Yield strength of WCC and LCC is specified to higher value of 275 megapascal minimum, and yield strength of LCB is specified to lower value of 240 megapascal minimum. So yield ratio of carbon steels, if we look at the yield ratio of yield strength to tensile strength of the ferritic steels, we can see the material condition for the heat treated. My understanding is that the full annealed ferritic steels usually indicated around 50% of yield ratio as a guide. It is supposed that WCB and A145 are almost heat treated with an annealing condition due to 51.5% of yield ratio. So we will talk about heat treatment for carbon steel. I assigned the description of the related on heat treatment derived from material specification. So ASTM A216 for WCB and WCC casting. Casting shall be furnished in the annealed or normalized and tempered condition. ASTM A115 heat treatment when required by 6.1 shall be annealing, normalizing and tempering, or quenching and tempering. So ASTM A352 for LCB casting and LCC casting. So two sections were indicated. 5.1 all castings shall receive a heat treatment proper to their design and chemical composition. It should be recognized that liquid quenching of the ferritic grade is normally required to meet the mechanical property of heavier sections and will greatly enhance the low temperature properties of thinner sections. 4.2 section is a normally requirement. Ferritic casting shall be furnished in the normalized and tempered or liquid quenched and tempered condition. So I summarize the table for heat treatment to each material: WCB, A115, WCC and LCC, LCB. And heat treatment specified heat treatment is writing down. So WCB casting, annealing or normalizing plus tempering. A115, annealing or normalizing plus tempering or quenching plus tempering. WCC casting, annealing or normalizing plus tempering. So LCC casting, normalizing plus tempering or liquid quenching plus tempering. LCB casting, same as the normalizing plus tempering or liquid quenching plus tempering. So A352 LCB casting and LCC casting both material for low temperature surface material, so that A352 material specification requires the heat treatment, normalizing or liquid quench. So normalizing and liquid quenching is heat treatment is material structure is become small, fine structure, become fine structure. So that tough, related on toughness property is very effective for normalizing liquid quenching. So WCB A105 WCC casting is used to be for middle temperature or relatively high temperature material, so that three different heat treatment specified, but usually we consider the annealed heat treatment condition, the WCB A105 and WCC casting. So annealing heat treatment is becoming the material structure is something coarse. Coarse structure is for good for high temperature. So next we talk about why is the yield ratio of LCB higher than that of WCB A105. So again we see the table. The LCB 240 megapascal minimum, and WCB A145 250 megapascal minimum. So LCB is used to low temperature application. Therefore, the material specification of ASTM A352 specified that normalizing or quenching heat treatment shall be conducted, and impact test is also conducted at minus 46.7 degrees Celsius temperature. In general, rapid cooling from austenitization temperature to ambient temperature, such as normalizing or quenching, promote to be fine material structure. It is supposed that LCB castings treated with the heat treatment of normalizing or quenching have a fine structure. From those results, they possess a relatively higher yield strength according to Hall-Petch equation. Hall-Petch equation suggests that a smaller grain size leads to greater yield strength. I assign the Hall-Petch equation here. So sigma y equals sigma 0 plus k divided by root of d, small d. Sigma y equals yield strength of polycrystalline material. Small d equal grain size. So sigma 0 is original strength of the related material, and k is also the coefficient of the based on the material. So root of D is small. D is the grain size. So grain size is increasing. So sigma y is decrease. Small d is small decrease grain size d grain size. So that sigma y illustrates higher value indicated. So this is a Hall-Petty equation. This equation is a very famous equation. Hall-Petty equation suggests that smaller grain size lead to greater yield strength. As a result, we can understand that LCB tend to have a higher yield ratio of 53.5% rather than 51.5% of WCB A105. So LCB casting received normalizing or quenching heat treatment, so that the structure is smaller than WCB A105. So either strength ratio, either strength is relatively high value, so that the ratio also high value indicated than WCB and A105. Next, why is lower tensile strength specified in LCB material? So again, we see the table. LCB casting material specified 450 megapascal tensile strength. This value is lower than another foam materials. Generally speaking, tensile strength is affected by carbon content. Normally thinking is that the decrease of carbon content in the carbon steel is accompanied by low tensile strength. When I worked related on the LCB casting before, I remembered that the material certificate supplied by the casting supplier indicated 0.14% to 0.15% of carbon content of LCB casting. I felt that the indicated carbon content in the material certificate was too low. The material supplier replied that carbon content should be reduced in order to attain the toughness at low temperature. I searched some article to confirm whether the information was accurate or not. The attached data, the attached chart showed that the reduction of carbon content was surely effective in improvement of toughness at low temperature in the normalized carbon steels. So this graph shows that horizontal axis indicate the temperature. So left side direction is minus temperature. So here is 0 degree Celsius, the freezing temperature, and minus 40 and 50, minus 50 areas, that areas here. So vertical axis indicated Sharpie V notch absorbed energy unit foot pound. So this indicated number, the carbon content indicated 0.8%, 0.69. So gradually decrease the carbon content number, so that the profile is indicated absorbed energy increasing the with reduce the carbon content. So toughness is increasing with decrease of the carbon content. So we consider about the so low temperature toughness something. Transient temperature is something considered. Transient temperature is about ductile fracture and brittle fracture is around 50-50. So that point is we call a transition temperature. And transition temperature is what temperature is indicated. So that around the half. This graph is a half point is a transition temperature here, 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 here. So transition temperature is decreasing temperature decreasing with the decreasing of the carbon content like this. So around the 0.11% carbon content, the transient temperature around 40%, 40 degrees Celsius, something here. So very effective the carbon content reducing to the low temperature toughness. So 0.8% carbon steel we call oitectoid carbon steel. So reduce the carbon content from 0.8 the carbon content we call hypo oitectoid steel. So the attached data showed that the reduction of carbon content was surely effective in improvement of toughness at low temperature in the normalized carbon steels. And also, I understood that the tensile strength of LCB casting was specified in lower value of 450 megapascal due to the lower carbon content. So LCB casting has a content of the carbon content very low, maybe 0.40% to 0.50%. This carbon content level is decrease of the tensile strength. So I understand this 450 megapascal minimum tensile strength for LCB casting, something reasonable, I think. Next, why is the yield strength of WCC, LCC higher than that of WCB 105? As shown in the attached table, The specified tensile strength of the WCB A105, WCC, and LCC are the same of 485 megapascal minimum, and the yield strength of WCC, LCC, and WCB A105 are specified 275 megapascal minimum and 250 megapascal minimum, respectively. We wonder why it is the difference of the yield strength specified between WCB and WCC, even though the same annealing heat treatment is required on them in the material specification. Again, we look at the table for the heat treatment. So WCB and WCC specified same heat treatment condition, annealing. It is supposed that fine grain size contribute to increasing the yield strength of WCC on the basis of hole pitch equation. So again, we look at the hole pitch equation. Sigma y is mean yield strength. Yield strength of WCC increasing. So small d grain size to be smaller. This is a hole pitch equation. Increasing of manganese assumed to help to be higher yield strength for WCC. The attached chart, this is attached chart, indicates that increasing of manganese brings about the fine prior austenite grain size. So this chart indicated the manganese content effect on grain size condition. So horizontal axis indicated the manganese content, and vertical axis indicated the austenite grain size number called ASTM number. So ASTM number increasing so that the grain size is to be fine. So increasing the number, grain size are smaller, indicate. So manganese content increasing, so the graph indicated the grain size is smaller size indicated. So manganese content around 1.5%, so indicated grain size ASTM number 7 to 8. 7 to 8 is something indicated smaller grain size. So grain size of gamma, gamma is mean austenite, is finer with increasing of manganese. Finer grain size induce increasing of yield strength by hole pitch equation. So for some reason, for the effect of the manganese will contribute. I'm not sure, but it is supposed that the grain size of prior austenite grain boundary become finer with the formation of compound of manganese sulfide. Manganese is high affinity with sulfur. It is assumed that the precipitate of manganese sulfide do not easily dissolve in the austenite phase at the austenitized temperature, and become nucleation of formation of austenite phase to lead to increasing of the fine austenite grain boundaries. I explain a little more related on austenite phase. Carbon steels indicate the mixed structure of ferrite and pyrite at the ambient temperature. When it is heated from the ambient temperature up to the austenitized temperature, around 900 degrees Celsius, 1600 degrees Fahrenheit to 1700 degrees Fahrenheit. Its ambient structure is transformed to austenite phase, we called gamma phase. This austenite grain boundary condition affects the material properties such as strength and toughness, so that we always consider about the grain size of austenite phase. The austenite phase produced in high temperature is transformed to ferrite and pyrite or martensite in case of the rapid cooling during cooling down to the ambient temperature. The austenite phase does not remain, but the austenite grain boundary leaves trace on the material structure after cooling down to the ambient temperature. So we called old austenite grain boundary or prior austenite grain boundary, which is revealed by the microscopic observation in the ambient temperature condition. So next, I talk about my experience related on effect of manganese content to increase yield strength of SL400B for building steels. In 2011, Japan had a very big earthquake in northern part area of Japan main island. The epicenter of the earthquake was around 500 kilometers away from here of Tokyo area. I felt the big shaking of the earthquake, even though here was far away from the epicenter. The earthquake was earthquake of seismic intensity 5 or upper 5 in here of Tokyo area. When I watched TV news at that time, the buildings which were projected on TV were swaying from side to side. The residents on the upper floors said that room was swaying to 1 meter to 2 meters, and they felt the earthquake shaking that made it difficult to stand. Surprisingly, even if the building was subject with the visible shaking, but they were not damaged. I supposed the steel frame materials which were used for the building construction were not SS400, which was very popular material for the steel structure, and some other structure steels, which had considerably high elasticity due to attain the flexibility and withstand distortion and breakage. The traditional steel structure material SS400 was plain carbon steel and indicated the property of typical low elasticity since it had low yield ratio of 51.3% calculated from yield strength to 105 megapascal minimum divided by tensile strength 400 megapascal minimum. After some searching for the building construction materials, I knew SN400B, which was a relatively new assignment of JIS standard and showed the high elasticity property was widely used for the building construction nowadays. SN400B indicated a higher yield ratio of 58.8%, and the elastic limit was also high, and also it has specified tensile strength 400 megapascal minimum and yield strength 235 megapascal minimum. According to the tensile strength 400 megapascal specified, it was supposed that SN400B was received with the annealed condition same as SS400. It was said that the plain carbon steels of the annealed condition indicated normally yield ratio of 50% of yield strength 200 megapascal and tensile strength 400 megapascal. I wondered why SN400B indicated high yield ratio 58.8% of yield strength 235 megapascal and tensile strength 400 megapascal with annealing heat treated. I realized that the chemical composition SN400B was same as WCC and LCC. So I was strongly aware of the necessity of manganese to increasing the yield strength. So we look at the chemical composition and mechanical property for the building structure. SS400 material and SN400B, two material assigned here. So SS400 material specifies only chemical composition, phosphorus and sulfur only. So carbon and silicon and manganese not specified here. But SS400 has a normally carbon content of 0.2% to 0.3%, like this. So SN400B, so carbon content 0.20% maximum, so relatively lower carbon content specified. So manganese 0.6% to 1.5% with a relatively high manganese content specified. How about mechanical property, tensile strength? Both material specified 400 megapascal minimum. So yield strength, SS400 indicated 205 megapascal minimum. This is a 400 megapascal tensile strength, around 200 megapascal minimum yield strength. This is a typically plain carbon steel for the annealed condition material. So yield ratio indicated 51.3, very low indicated yield ratio. But SN400B indicated yield strength 235 megapascal minimum, and yield ratio in calculated 58.8%. This number is relatively high yield ratio indicate. So also material specification specify the yield ratio 80% maximum specified. This number 80%. For me, I usually use pressure retaining material. So this area is not is so unusually case of the specified of the yield ratio. 80% maximum specified case is a rare case in a pressure retaining material area. But building construction material area is specified yield ratio limitation, 80% maximum. Yes. So anyway, I was strongly aware of the necessity of manganese to increase the yield strength. So yield ratio 80% maximum was specified in SN400B. I thought that SN400B was considered to be applied in the plastic deformation zone. It was supposed that the specified yield ratio 80% maximum intended to suppress the yield strength in order not to be closer to the tensile strength. The tensile strength is mean breakage stress. Next, we discuss about the tensile strength and yield strength for the carbon steel grade WCB, WCC, LCC, and LCB casting material. I assigned the two charts showing the relationship between the yield strength and temperature for the carbon steel casting. So the right side chart indicated the relationship between tensile strength and temperature for the carbon steel casting. So left side indicated the yield strength curve. So horizontal axis indicated the temperature and the vertical axis indicated the yield strength. So unit megapascal. I collect the data from the ASME section 2 part D for material WCC, LCC, WCB, LCB. So I plotted the data here. So WCC and LCC casting materials have a same yield strength value over the whole temperature range. So the curve for the same profile. So WCC and LCC is a higher yield strength level than the other two materials. So that's the cause of the manganism effect, as just before saying. So blue line indicated the WCB, and yellow curve indicated the LCB material. So LCB casting have a still lower yield strength. So right side chart indicated the tensile strength curve. So gray curve indicated the WCC and LCC and WCB. So three materials together have a same tensile strength value, whole temperature region. So plotted the same curve. So yellow curve for LCB curve. So LCB has a still low tensile strength, so whole temperature region. So that temperature dependability of yield strength is shown in the left side chart. So stable profile of tensile strength is shown against the temperature up to 400. So that's the constant and stable value indicated. After or over 400 degrees Celsius, so increasing the temperature rapidly decrease on the both four materials. These curves of yield strength and tensile strength resemble the curve of the allowable working pressure for standard class and special class as shown just before. So again, we look at the allowable working pressure curve. Here, this standard class 300 allowable working pressure curve, very likely with the yield strength curve. And this special class 300 allowable working pressure curve. This curve is very likely with the tensile strength curve. The stable temperature is 350. Tensile strength is stable temperature 400. So it is suggested that the curves of tensile strength versus temperature show that the hardnesses of the quenched materials are not changed or decreased, even though the tempering heat treatment is conducted on them below the temperature of 400 degrees Celsius. So that tensile strength is stable, not changing. Equal hardness also not changing. So if in case the heating up to the 350 temperature as a tempering, low temperature tempering, but not changing the hardness. But yield strength curve is changing, 350. So yield strength level is decreasing. Generally, the carbon content in the materials exerts influence on their tensile strength. In case of heated up more than 400 dC, carbon element and also other elements becoming a big movement in the material structure due to their diffusion rates activated by the heated. If the carbon element and other elements leave the material structure, matrix structure, and they produce the carbide. The tensile strength is reduced as shown the curve, like this curve. So reduce the curves. Here, from here, we discuss about the effect of the temperature dependability of tensile strength and yield strength on tempering heat treatment. The The multensitic stainless steels such as grade 410, 403, 416 are hardened by heating at austenitizing temperature around 1000 degrees Celsius, 1800 Fahrenheit to 1900 Fahrenheit. For cooling in the air oil. After the materials have cooled below the multensite finish temperature, called MF point, they should be tempered as soon as possible. Depending on hardness, strength, or toughness requirement, the materials are tempered in low temperature below 400 or high temperature above 600 degrees Celsius. Tempering in the range 800 Fahrenheit to 1100 Fahrenheit should be avoided because temper envelopment or lower toughness will result. Low temperature tempering below 400 degrees Celsius is usually applied for the valve trim parts to keep quenched hardness. On the other hand, high temperature tempering above 600 dC is applied for the mechanical structural parts to reduce hardness and to get stress relaxation and to attain the good toughness. It is said that in case of carbon steels or ferritic alloy steels, the carbon contained cannot be large movement in metal matrix structure below temperature of 400 degrees Celsius due to inactive of its diffusion. However, above temperature of 400 dC, the diffusions of carbon and other elements become more active and they easily leave the matrix structure to form carbides, which are compound of some high affinity element for carbon. If the carbon leaves the matrix structure along with decrease of its content in that matrix above 400 dC, tensile strength or hardness of the material is decreased as shown in the attached chart for relationship between the tensile strength and tempering. So again here says, so tempering heat treatment is usually conducted to stress relaxation after hardening by quenching heat treatment. In case of high temperature tempering above 600 dC and more, quenched hardness is reduced along with reduction of tensile strength. In case of low temperature tempering below 400 dC, the quenched hardness is maintained and not decreased since the tensile strength is kept constant as shown in the attached curve of tensile strength versus temperature. So here stable tensile strength is stable here. However, the role of low temperature tempering releases the peak stresses, which are internal stresses induced by quenching heat treatment. These induced peak stresses are antagonistic to the yield stress at that temperature. Therefore, the peak stresses can be reduced according to the reduction of the yield strength with increasing temperature as shown in the attached curve of yield strength. So that yield strength curve here. So low temperature tempering if the 350 heating up to the tempering process. So the materials decrease the ego strength decrease the in case of a WCC case from 280 megapascal to 200 megapascal reduced here. So balanced internal stress also reduce the 200 megapascal. Ambient temperature, internal stress and ego strength are balancing. So internal stress has a 280 megapascal stress, but heating up to the 350, so decrease of the ego strength, also internal stress reduced to the 200 megapascal. After recovery to the ambient temperature, so ego strength recovery the original ego strength at ambient temperature 280, but internal stress relaxed to the still 200 megapascal level. So relaxation the internal stress. This is a low temperature tempering process. So again, this induced peak stress antagonistic to the ego stress at that temperature. Therefore, the peak stress can be reduced according to the reduction of ego strength with increasing temperature as shown in the attached curve of ego strength. From here, this case is my experience. Talking about that. Sometime in the past, a heat treatment operator engineer asked me about the tempering heat treatment for the 403 Mountainside stainless steel. He said that the hardness was not decreased and remained on the quenched hardness even though the tempering heat treatment at the temperature of 300 DC to 350 DC was conducted on the quenched hardened material. He raised the question about useless or needless of the low temperature tempering because of no any changing of the hardness. I thought that almost people normally recognized that the tempering process needed to achieve decreasing of the hardness. I have to say the important role of the low temperature tempering even though the hardness was not changed. Both the internal stress induced by the quenching hardness process and the ego stress were balanced at the cooling down to ambient temperature. As quenching hardened material possessed very high internal stress, which was same level as the ego strength at the ambient temperature. That material in such situation suffered damage with receiving a small amount of external force, which was caused of easily exceeding ego stress. The low temperature tempering needed to be conducted to reduce the high internal stress. From here, we discuss about method for establishing standard class and special class pressure temperature rating. So I assigned the clipping of the description of method for rating class. from ASME B16.34. So B-2 standard class rating method. So and also B-3 special class rating method. So different method for standard class and special class. So B-2.1 method for group 1 materials. So in case of group 1 materials, so pressure temperature ratings for standard class valve, class 300 and higher, or materials listed in table 1. Material group 1 were established by the equation. This equation calculated the PST equal standard class rated working pressure. This is the working pressure. And C1 is a coefficient of, usually we assign the 10, when S1 is a selective stress, is expressed in megapascal unit. So we usually use a megapascal unit. So we use C1 equal 10. S1 is a selective stress. S1 is a selective stress. This is a very important factor for determining the working pressure. So denominator number 8750 indicated, and multiply PR. PR is mean pressure class rating index. In case of rating class 300, we assign the PR equal 300. And PCA is the saving pressure at temperature T, as specified in section B5 for standard class. So this saving pressure indicated the maximum allowable working pressure in any case. So calculated PST allowable working pressure cannot be exceed this PCA. So this is the maximum allowable working pressure indicated. So S1 selective stress megapascal for the specified material at temperature T. The value of S1 shall be established as follows. So A, at temperature below the creep range, S1 shall be equal to or less than 60% of the yield strength at temperature T, but shall not exceed following. So 1.25 times 25% of the ultimate tensile strength at temperature T. So easily thinking which one is lower value to be selected. So creep range is considered to be at temperature in excess of 370 degrees Celsius for group 1 materials. So the ultimate tensile strength and yield strength values shall be as listed in ASME section 2 part D. And also allowable stress values listed in ASME section 2 part D, like this. So method for group 2 and 3 materials, it's the same here. 60% factor shall be changed to 70%, and for group 2 materials, the creep range is considered to be at temperature in excess of 510 degrees Celsius. In case of the special class rating method, this equation here, so PSP is a special class rated working pressure. So C2 is also coefficient. So we usually use 10 when S2 is selected stress expressed in megapascal. So we use C2 equal 10. So S2 is selected stress for the special material at temperature T. So, and denominator number 7,000. So standard class 8,750, but the special class 7,000 indicated in the denominator. Multiply PR. PR is the rating, bulb rating class number. So, and PCB also the sealing pressure. So that maximum working pressure. So in any case, calculated PSP cannot be exceed this number, these values. So how about selected stress S2? This is an important factor for working pressure. So the value of S2 shall be established as follows. At temperature below the creep range, S2 shall be equal to or less than 62.5% of the yield strength at temperature T, but shall not exceed following. So number 2, 25% of ultimate tensile stress value at temperature T. So standard class, so yield 60% of the yield, but the special class 62.5% of the yield strength. Also tensile strength 1.25 times 25% of tensile strength, but in case of special class 25% of ultimate tensile stress value at temperature T. The creep range is to be considered that at temperature in excess of 370 degrees Celsius for group 1 material, same as the standard class, and 510 degrees Celsius for group 2 material. So that maximum ratings, this is related on sealing pressure. The rules for establishing standard class and special class pressure temperature ratings, including consideration of sealing pressure PCB or PCB that effectively set limit on the selected stress. The sealing pressure temperature values set an upper bound for high strength materials and are imposed to limit deflection. So I arranged the equation for standard class and special class. So again, that PST standard class rated allowable working pressure C1 coefficient 10 when S1 is expressed in megapascal. PR pressure rating class index. So designation number class 300, so we assign the PR 300. PCA, failing pressure, bar at temperature T for standard class. The failing pressures indicated the upper limit working pressure. The calculated values are not adopted for the pressure temperature ratings, even though the working pressure for high-strength material are calculated and higher than the failing pressure indicated in Table B3. S1, selected stress for standard class, megapascal to temperature T for specified materials. So number 2, equation for special class. So like this same special class rated allowable working pressure. So that same as before. So here is we talk about again determine the selected stress S1 and S2. I arrange the summarize the selection of selected stress S1 and S2. Creep range in excess 370 degrees Celsius for group 1, in excess 510 degrees C for group 2, and determined on an individual basis for group 3. Temperature below the creep range for material group 1. The value of S1 shall be established as follows. Lower one is adopted as selected stress. 1. 60% of the specified minimum yield strength at temperature at ambient temperature. 60% of yield strength at temperature T. 1.25 times 25% of the ultimate tensile strength at temperature T. Allowable stress at temperature T in creep range excess 370 degrees Celsius. For material group 2 and 3, 70% of the specified minimum yield strength at temperature 38 degrees Celsius. 70% of yield strength at temperature T. 1.25 times 25% of the ultimate tensile strength at temperature T. Allowable stress at temperature T in creep range excess 510 degrees C for group 2. At temperature in the creep range for material group 1, 2, and 3, the value of S1 shall be the allowable stress at temperature T as listed in ASME section 2 part D, but not exceeding 60% of the listed yield strength at temperature. So in case of the special class, creep range is same as the standard. So for material group 1, 2, and 3, at temperature below the creep range, the value of S2 shall be established as follows. Lower one is adopted as selected stress. 62.5% of the specified minimum yield strength at temperature 38 degrees Celsius. 62.5% of yield strength at temperature T. 25% of the ultimate tensile strength at temperature T. Allowable stress at temperature T in creep range excess 370 degrees Celsius for group 1 and 510 degrees Celsius for group 2. At temperature in the creep range, the value of S2 shall be the allowable stress at temperature T as listed at ASME section 2 part D, but not exceeding 62.5% of the listed yield strength at temperature. So from now, we talk about assuming the reason why for the difference of the temperature dependability between standard class and special class on the allowable working pressure. Again, we look up the allowable working pressure curve. This is for yield strength curve, and this is a tensile strength curve. This is a standard rating class 300 working pressure temperature curve. This is for a special class. So working pressure curves like this. So likely, so standard class is very likely for yield strength curve, and special class working pressure curve is very likely the tensile strength curve. Yeah. So suppose that yield ratio is 50% for group 1 material and 40% for group 2 and 3 respectively, and tensile strength is 1.0. For group 1 material, selected stress S1 for standard class. Yield strength is suppose assign the 50% of group 1 material, and standard class indicated 60% of the yield strength temperature. So 0.5 multiply 0.6 equal 0.300. Tensile strength assign the 1.0. 1.0 multiply standard class indicated 1.25 times 25% of ultimate tensile strength. So 1.0 multiply 1.25 multiply 0.25 equal 0.3125. So yield strength, so in case of the yield strength, lower value indicated than tensile strength. So the calculated allowable working pressure selected stress calculated S1 may be controlled controlled by the yield strength values. So selected stress S2 for special class. Yield strength 0.5 multiply 0.625. In case of a special class, 62.5 of the yield strength. So 0.5 multiply 0.625 equal 0.3125. How is tensile strength? 1.0 multiply 25% of the ultimate tensile strength. So multiply 0.25 equal 0.2500. So tensile strength value indicated lower than yield strength. So that selected stress S2 controlled by the tensile strength values. So PST, the working pressure, calculated working pressure for standard class may be determined depending on the yield strength here. So PSP, the working pressure, the calculated working pressure for special class may be determined depending on the tensile strength here, tensile strength here. So we understood that here we understood that standard class rating curve is very likely the yield strength curve is like that. So special class rating curve likely for tensile strength. That is very understandable here. So for group 2 and 3 material, selecting strength S1 for standard class. Yield strength so that the 40% of the yield ratio. So 0.4 multiply. So standard class for 70% of yield strength. So multiply 0.7 equals 0.80. How about tensile strength? 1.0 multiply 1.25 times 25%. So 0.3125. So suppose that select stress S1 may be controlled by yield strength values. Selecting stress S2 for special class. Yield strength 0.4 multiply 62.5% of yield strength. So 0.4 multiply 0.625 equal 0.2500. How about tensile strength? 1.0 multiply 25% of ultimate tensile. So calculate number 0.25. The same value indicated. So allowable working pressure for standard class may be determined depending on the yield strength here. So working pressure for special class may be determined depending on either yield strength or tensile strength. Here we look at the ceiling pressure, PCA standard class ceiling pressure. Table B3 ceiling pressure derived from ASME B16.34, A standard class and B special class. So very detailed indicated ceiling pressure for temperature and each rating class. Right. So this number indicated the ceiling pressure, the maximum working pressure. So the calculated working pressure cannot be exceeding these numbers. So the ambient temperature, the working pressure, we call the cold working pressure, CWP. So standard class ceiling pressure of ceiling cold working pressure, this. Also, special class is the same value indicated. So in case of the special class, so ceiling pressure is not so much degrees, around 400 degrees Celsius. So almost same value indicated. But standard class for ceiling pressure decreasing with increasing the temperature. So decreasing. So we try about calculation of allowable working pressure of rating class 300. So this table indicated for standard class 300 for WCB casting. So lower table indicated special class 300 for WCB casting. So the table indicated a comparison table of calculated and tabulated allowable working pressure of standard class 300 for WCB. So that PST, the allowable working pressure for standard class. So equation right here. So C1 equal 10. We use a megapascal. S1 indicated with bold font. PR equal class 300. So assign the 300. So that C1 is 10 and the PR is 300. So S1 value is something considered. So temperature is indicated 38, 100, 150 like this temperature. So yield strength and tensile strength. So data taken from ASME section 2 part D. So yield strength data assigned here. So tensile strength data right down here like this. So for the standard class, 60% of yield strength specified in ASME B16.34. So yield strength multiply 0.6. So calculate number indicated here. So 1.25 times 25% of tensile strength specified in ASME B16.34. So that calculates number assigned here. So we compare with the yield strength value and tensile strength value, which value is lower. So that 150 is lower than 151.6. So we assign this number for selected stress S1. So I indicated with a bold font. So compare with this number. So still yield strength multiply 0.6 is a lower value indicated. So that like this. So 370 is a border temperature for a creep range. So creep range is indicated to be indicated allowable stress. So allowable stress value indicated here taken from ASME section 2 part D. So like this. So the 375. So consider the allowable stress value. So compare with the other values. So still lower value for yield strength multiply 0.6. So 160.2 assigned for S1 selected stress. So indicated with the bold font. So 400 dc is the allowable stress value indicated lower value than other. So 101 megapascal, and 83.9 is the lower value. So assign the selected stress S1. So the indicator is bold font like this. So calculate the PSD. Substitute the bold font value to dash S1. So calculate the number, calculate PSD number here, assigned here. So 51.4, 46.7, 45, 41.1 something. So try to compare with the formal allowable working pressure. So tabulated pressure in table 2. This number is a formal working pressure. So compare with the calculated number. Almost same number are indicated like this. So that this calculation is I think okay something. So how about ceiling pressure? So I assign the ceiling pressure for standard class 51.7 like this ceiling pressure. So the assign the tabulated pressure, also calculated pressure do not exceed the ceiling pressure. It is okay. Something. So that lower table for special class 300 for WCB. So yield strength and tensile strength same as the standard class member like this. So 62.5% of yield strength specified for special class. Also 25% of tensile strength specified for special class. So this calculated number indicated here. So compare with the yield strength number and tensile strength number, and which one lower value indicated. In this case, tensile strength multiply 0.25 is the lower value indicated. So indicated with bold font. So 325 to 375. So that yield strength value is lower than tensile strength. So assign the selected stress S2 assigned. So with the bold font. So that 370 border temperature for creep range. 375, 117. So still lower value indicated for yield strength level. So assign the 110.6 is assigned for S2 with the bold font. And temperature 400 and more, allowable stress value, lower value indicated than others. So assign the S2 selected stress with indicated bold font. like this. So calculate the PSP number. So the 52 0 bar, 51 8.8 bar, like this. So that compare with the tabulated pressure, 51.7, 51.6. So tabulated pressure is indicated lower value setting. So calculate number is still higher value indicated. So ceiling pressure for special class. So indicated here. So 51.7 indicated ceiling pressure. This is the maximum allowable working pressure. So calculate number is higher than ceiling pressure. So that formal working pressure indicated ceiling pressure for 51.7 and 51.6 something. So something this something lower value setting up. I'm not sure about. So that 350 degrees Celsius, almost same the calculate number and the tablet pressure. So almost same, both calculate number and tablet pressure same. Next is in case of the standard class 300 for WCC casting. So lower table for special class 300 for WCC casting. Same manner is indicated. So yield strength and tensile strength for WCC casting taken from ASME section 2 part D. So indicated here, and tensile strength also here. So standard class 60% of yield strength and tensile strength for standard class 1.5 times 25% of tensile strength. So this calculated number sign here. So compare with the yield strength and the tensile strength, which one is lower value indicated. The ambient temperatures indicated tensile strength level 151.6. So this is assigned the S1 selected value. So 100 to the 375 indicated a lower value for yield strength marked by 0.6. So indicated with bold font for S1 assignment. So 375. So allowable stress value indicated here. So 375 still yield strength value is lower indicated than allowable stress. So assign the 170.6 assigned for S1 value. So indicated with bold font. 400 temperature and more. So allowable stress value, lower value indicated. So we assign the S1 value for this. So with bold font. So calculate the PSD number right down here. 52.0 bar, 51.6. So that tablet value pressure 51.7, 51.6, 51.2, 416. So that ceiling pressure for standard class, so assigned here. So compare with the ceiling pressure, tablet pressure, and calculated pressure compares. So the tabulated pressure, formal assigned the pressure indicated with the ceiling pressure. So that's something. So WCB casting is for allowable working pressure dominated by ceiling pressure for standard class. So 375. So that the allowable working pressure is controlled by the controlled. So the special class 300. Unit strength multiply 0.625 and tensile strength multiply 0.25. So calculate the number assigned here. So compare with this number of which one's lower value indicated. So that in case of special class, tensile strength multiply 0.25 is lower value indicated. So assign the S2 selected variable. So indicated with the bold font. How about creep range temperature 370? So we have to assign the allowable stress. So allowable stress value indicated here 123. So that tensile strength multiply 0.25 is still lower value indicated. So 400 degrees Celsius and more. So allowable stress controlled the lower value indicated. So assign the S2 selected value with bold font. So calculate the PSP number here, assign here. So we compare with the tablet pressure and ceiling pressure. So ceiling pressure here. So tabulated pressure for a special class. Almost same value indicated for ceiling pressure like this. And 350 is something lower, and 400 degrees Celsius over temperature with calculated PSP is same as almost same as number indicated for tabulated pressure. This is table for LCC casting. So WCC, LCC casting and WCC casting the same property, tensile strength, yield strength, same property. So that the completely same as the WCC casting. This is something different. Is temperature limitation indicated here. So allowable stress value indicated so temperature limitation 375 to the ASME section 2 part D. So LCC casting material to be used for pressure retaining material up to 375 degrees Celsius. So 400 degrees Celsius cannot be used for LCC casting. So how about the barrel material? So ASME B16.34 also have a temperature limitation. So ASME B60.34 indicated temperature limitation for 345 degrees Celsius commented in table 2, 1.2. This is ASME B16.34. So in case of using barrel material, wood cannot be used for LCC material 350 degree temperature, only 345 degrees Celsius. So that calculate PST value and also tabulated pressure value is same as the WCC cast. In case of special class, also same as the WCC casting. So in case of the LCB casting, upper table for standard class 300 for LCB casting, lower table indicated the special class 300 for LCB casting. So yield strength and tensile strength data taken from ASME section 2 part D and indicated here. So that same manner for the yield strength multiplied by 0.6, tensile strength multiply 0.25, multiply 1.25. So compare with the calculated number, which one lower value indicated. So that 38 degrees Celsius tensile strength value is the lower value indicated. So assign the S1 number and 100 and 150 something to 375. So the yield strength value indicated the S1 selected value with bold font. So also LCB casting material also have a temperature limit. So ASME section 2 part D allowable stress value only 375 degrees Celsius. So 400 over more temperature. So no assign the allowable stress. So we can use LCB casting up to 375 for pressure retaining material. But in case of the bulk material, ASME B16.34 specify the temperature limit for 345 degrees Celsius. So in case of we use for bulk material, so temperature limit 345 degrees Celsius. So calculate PST and tablet pressure, almost same value indicated. So also pressure, working pressure for special class 300 or LCB. This is also calculate number same as the tablet pressure. So temperature limit the 345 degrees Celsius. Even those are special class temperature limit for LCB casting. So next is we try to calculation of allowable working pressure of rating class 300 for CA6mm casting. This casting material is not listed in ASME B16.34. So if CA6mm casting material assigns the ASME section 2 part D for allowable stress indicated in CA6mm. So in case of the pressure retaining material, we can use this casting material, but not listed in ASME B16.34. So in case material cannot be used for that material, but in case of the rating table is assigned for the CA6mm, so that we can use for bulk material. So we try to the rating table for CA6mm for rating class 300. So that upper table indicated for standard class 300 for ASTM A487 CA6. So lower table indicated the special class 300. The same manner, the calculate the allowable working pressure PST. So PST and PSP is the same manner, same equation. So that yield strength and tensile strength taken from section 2 part D and write down here. So yield strength levels very high, 550 megapascal, very high yield strength indicated for casting CA6mm. So tensile strength of the higher level. So calculate the 60% of yield strength. So 330.0, 310.2. So indicate the calculated value here. Tensile strength multiply 25% and 1.25 times. So calculate number 237.5. Like this number, calculate number indicated here. So compare with the yield strength and tensile strength. Tensile strength value is the lower value indicated. So assign the S1 selected value assign with the indicated with the bold font up to the 350. So 375. So allowable stress value. So that control the allowable stress value to assign the S1 here. So that section 2, part D indicated allowable stress value and also yield strength, tensile strength value up to the 450 degrees Celsius for CA6 and M. So in case of the pressure retaining material, we can use up to the 450 degrees Celsius. So in case of the bottom material also assign the ASME section 2 part D specified temperature limit. So calculate the PST 81.4 very high working pressure calculate. So that ceiling pressure for standard rating. So compare with the calculated number and ceiling pressure. So still lower indicated ceiling pressure. So we have to assign the allowable working pressure for tabulated value. So 51.7 comes from ceiling pressure. So maximum ceiling pressure, working pressure 51.7, 51.1, 15. So assign here. This number for allowable working pressure for standard class 300 for material CA6NM. So we complete the rating table for the standard class 300 for CA6NM. This number indicated. So also special class also the calculated PST like this very high working pressure calculated. So that we have to assign the ceiling pressure for a special class. Like this number assigns for the tabulated allowable working pressure for special class 300 for CA6NM. So that's all for I have for today. I will talk about equation of wall thickness calculation for pressure retaining parts with the next video, number 4. Thank you very much for watching.